Most stars die the slow death of a candle, burning steadily and then fading into blackness. But the most massive stars go out with a bang, collapsing in on themselves before exploding outward in a supernova that blasts stellar material into the universe. The core of the star implodes, and if its mass is greater than our Sun's, collapses all the way down to a fraction of a mile in diameter. Gravity overwhelms all other forces, crushing protons and electrons together to form neutrons and forcing them into an infinitely dense point called a singularity. Some of the star's mass is blown away in the explosion, but most is compressed into an incredibly dense sphere called a neutron star. Neutron stars are so dense that a teaspoon of their material would weigh billions of tons. They are also fast rotators, spinning hundreds of times per second, and many are equipped with powerful magnetic fields. Imagine taking a mountain and squeezing it down to the size of a sugar cube. That's how incredibly dense neutron stars are. A single teaspoon of matter from one of these collapsed stars would weigh about the same as 200 million tons of matter here on Earth. But how do astronomers learn anything about such strange objects? One key is to find neutron stars in action, like the supernovas that gave birth to them, or the pulsars and magnetars that they power. Supernovas were first sighted in the 16th century when Tycho Brahe saw the guest star in the constellation of Cassiopeia. It was not there when he had observed the sky a decade earlier. Early astronomers did not know what these bright spots of light were, or why they appeared and disappeared over the years. But today, we understand that these transient events are the dramatic deaths of massive stars and that they play a critical role in the universe. The brightest supernovas, known as Type II, occur when the core of a massive star collapses in on itself, triggering a shockwave that blasts material into space. This leaves behind a rapidly rotating neutron star, which emits an intense burst of radiation as it forms. As the debris from the explosion clears, the neutron star is revealed. Depending on its mass and rotation rate, it may enter a phase known as a pulsar, emitting beams of electromagnetic radiation from its magnetic poles. These pulsars appear to us as rapidly blinking stars. Others are equipped with even stronger magnetic fields, creating gigantic magnetized stars known as magnetars. Another key to understanding neutron stars is unraveling the structure of matter under extreme conditions. At the heart of a neutron star, matter exists in a state that we cannot recreate on Earth. Here, the familiar world of atoms dissolves. Protons and electrons are crushed together so tightly that they combine to form neutrons. In this realm, the only constituents of matter are neutrons, and they are packed together much tighter than in atomic nuclei. While atomic nuclei typically have a radius of about 3.6 femtometers, the radius of a neutron star is around 12 kilometers. On the surface, neutron stars are no more than exotic balls of nuclear matter, yet their interiors are thought to be divided into several layers, each with its own unique properties. The outer crust, which extends from the surface down to about 100 meters, is made up of a neutron-rich fluid in which some neutrons have been converted into protons and electrons. Below that is the inner crust, extending to a depth of about 1 kilometer, where the fluid becomes a lattice of neutrons and exotic particles known as hyperons. Finally, at the very core, matter exists in a state that is still not well understood, but is thought to be in a state of complete nuclear matter. And what makes neutron stars even stranger is that they come in a variety of shapes and sizes. Some are nearly perfect spheres, while others are shaped like American footballs. They can rotate up to 600 times per minute, and some emit powerful bursts of radiation known as soft gamma repeater bursts. These strange objects have challenged our understanding of gravity, nuclear physics, and the behavior of matter under extreme conditions. Yet they have also given us a glimpse into the workings of the universe and the origins of some of the heaviest elements on the periodic table. By studying neutron stars, we are learning about the fundamental laws of nature and the evolution of the cosmos. Today, we can detect gravitational waves produced by the collision of neutron stars, and these signals carry information about the stars themselves, such as their mass and spin. Scientists hope that future detectors will be sensitive enough to measure the ringing of neutron stars after they collide, providing unprecedented insights into their structure. These tiny signals carry within them the secrets of the universe, and those who decipher them will unlock new understandings of the fundamental laws of nature. When you think of stars, you might imagine glowing balls of gas suspended in the vast darkness of space. Have you ever wondered what happens to these stars when they die? Places where matter is squeezed to unimaginably high densities, and gravity is so intense that not even light can escape its grasp. Welcome to the world of neutron stars, celestial objects so dense that a teaspoonful of their material weighs billions of tons. To understand how these stellar corpses come to be, we have to start with the very stuff of stars. The plasma that glows and shimmers as it undergoes nuclear fusion, converting hydrogen to helium, carbon, oxygen, and eventually iron. This process generates the outward pressure that counteracts the inward pull of gravity. But once a star runs out of hydrogen, things begin to change. Gravity starts to get the upper hand, and the star's outer layers begin to collapse. This triggers a series of events that literally shakes the cosmos. The core of the star collapses so rapidly that protons and electrons are forced together under immense pressure, combined to form neutrons, a process known as neutronization. This sudden shift in composition generates an intense burst of neutrinos, ghostly particles that zip through the universe barely interacting with anything. These neutrinos carry away a tremendous amount of energy as the star rebounds from the depths of its collapse. This explosive release of energy blasts the outer layers of the star into space. It is one of the most violent events in the universe, visible for millions of light years as a supernova. What remains after this cataclysmic event is a core of neutrons. Imagine squeezing the entire mass of the sun into an object only 20 kilometers across. That's what a neutron star is, an incredibly dense sphere of neutrons held together by the strong nuclear force, the strongest force in nature. But the question arises, why don't these neutron stars simply collapse into black holes? The answer lies in the strange rules that govern the behavior of matter at the atomic level. You see, inside a neutron star, the neutrons are packed so tightly together that they can't fit any closer. This might sound counterintuitive, but it's due to a quantum mechanical rule known as the Pauli exclusion principle. This principle states that two fermions, particles like neutrons, which have a half-integer spin, cannot be in the exact same state. In other words, each neutron in a neutron star has its own unique quantum state. It's like trying to pack identical balls into a box. You can arrange them in different combinations, but you can't pack them infinitely close together. This exclusion of neutrons from each other's space creates a kind of pressure called neutron degeneracy pressure. And this pressure is strong enough to halt the collapse of a neutron star. But the conditions within a neutron star are so extreme that matter behaves in ways we do normally associate with everyday life. Under such intense pressures and in the complete absence of air, neutrons don't just sit still. They move around. In fact, they move incredibly fast. So fast that if you were to look at a neutron star's surface, it would appear to be moving in a strange, constantly shifting pattern. This strange behavior gives rise to one of the most recognizable features of neutron stars, pulsars. These celestial objects are like cosmic lighthouses, emitting beams of radiation that sweep across space as the neutron star rotates. Imagine standing on a rotating carousel, holding a flashlight, and pointing it at a wall. As the carousel turns, the beam of light sweeps across the wall. Pulsar beams are created in a similar way. Charged particles accelerated along the neutron star's magnetic field lines generate electromagnetic radiation that focuses into beams near the poles of the star. When these beams hit our line of sight, we observe a pulsar. And because neutron stars rotate so rapidly, typically thousands of times per minute, these beams of radiation sweep across our sky at a steady rate, giving us a precise clock-like signal. Pulsars are not only fascinating astronomical phenomena, but also serve as incredibly useful tools for measuring distances in space. By studying the timing of pulsar signals, astronomers can map the positions of objects in our galactic neighborhood with great accuracy. But the variety of neutron stars doesn't end there. There's another class of these celestial objects that are even stranger: magnetars. Magnetars are neutron stars with exceptionally powerful magnetic fields, trillions of times stronger than Earth's magnetic field. These colossal magnetic fields arise during the initial collapse of the star, when charged particles are driven by the dynamo effect to create powerful currents in enormous magnetic structures. The magnetic field of a magnetar is so strong that it can strip atoms of their electrons, creating a sea of ionized gas around the neutron star. As charged particles move through this ionized gas, they accelerate, generating X-rays and gamma rays. This process makes magnetars some of the brightest sources of high-energy radiation in the universe. One of the most compelling aspects of magnetars is their role in some of the most extreme environments in the universe. The colossal magnetic fields of magnetars can reach up to 1 trillion times the strength of Earth's magnetic field. To put this into perspective, if we scale up Earth's magnetic field to the strength of a magnetar, the magnetic force would be so strong that it would completely rip apart atoms. This process of stripping atoms of their electrons leaves behind a cloud of ionized gas around the neutron star. As charged particles navigate this sea of ions, they are accelerated, and this acceleration generates intense radiation, making magnetars some of the brightest sources of high-energy radiation in the universe. But while pulsars and magnetars offer a glimpse into the strange behavior of neutron stars, there's another class of these celestial objects that truly pushes the boundaries of our understanding. Enter binary neutron star systems. These systems consist of 2 neutron stars that orbit each other, locked in a celestial dance of gravity and nuclear physics. The study of these systems provides an extraordinary window into some of the most energetic phenomena in the universe. As 2 neutron stars orbit each other, their intense gravitational pull distorts their shapes, creating tidal waves of matter that spill over the stars and crash into each other in a continuous cycle of intense heat and radiation. These collisions generate gravitational waves that ripple through the fabric of spacetime. The first detection of gravitational waves in 2015 provided direct evidence for the existence of binary neutron star systems, confirming a major prediction of Einstein's theory of general relativity. But the story doesn't end there. Binary neutron star systems are also responsible for creating some of the heaviest elements in the universe, including gold and platinum. When 2 neutron stars collide, the intense heat and pressure forge these heavy elements in a process known as the Rapid Neutron Capture Process, or R process. The debris ejected from the merger forms a cloud that enriches the surrounding space with heavy elements, contributing to the chemical diversity of the cosmos. In a way, these systems are cosmic laboratories where the fundamental laws of nature are tested and where the building blocks of life are forged. Understanding these systems allows us to peer into the very heart of matter and gravity, unraveling some of the deepest mysteries of our universe. Binary neutron star systems are not only astrophysical wonders, but also serve as testing grounds for some of the most fundamental laws of physics. These systems allow us to study extreme gravity, the behavior of matter under extreme conditions, and the nature of gravitational waves. Furthermore, they play a crucial role in understanding the origin of heavy elements in the universe. The intense energy released during the collision of 2 neutron stars can forge elements as heavy as gold and platinum. These elements are then dispersed into space, seeding the cosmos with the building blocks of life. In exploring binary neutron star systems, we are not only unraveling the mysteries of the universe, but also gaining insights into our own existence. The very elements that make life possible were forged in the hearts of these celestial objects. Studying them helps us understand where we came from and what we are made of. The future of neutron star research holds many exciting possibilities. With new and improved telescopes, we can observe these objects in greater detail than ever before. Gravitational wave detectors are becoming more sensitive, allowing us to detect signals from merging neutron star systems more easily. Theoretical work is also advancing our understanding of neutron star structure and behavior. As we continue to explore these enigmatic objects, we can expect to uncover even more fascinating insights into the nature of our universe. Neutron stars are a testament to the incredible power and diversity of our universe. They remind us of the incredible forces that shape the cosmos and the amazing discoveries that await us as we continue to explore the mysteries of space. Neutron stars are some of the densest, most extreme objects in the universe. It's just a quick refresher. A neutron star is what remains after a massive star goes supernova. All that's left of the star is its core, which is compressed to incredible densities and is mostly made up of neutrons. Astronomers know that these objects exist because they've witnessed the spectacular supernova that give rise to them. They've seen the pulses of radiation emitted by many neutron stars, known as pulsars, and they've directly detected the gravitational waves produced when two neutron stars collide. But despite all that indirect evidence, astronomers have never actually captured a picture of a neutron star. That is, until now. The breakthrough images of a neutron star were taken by the Chandra X-ray Observatory and the Hubble Space Telescope. The object pictured is named M82, or NGC 6624. It's a pulsar in the middle of a supernova remnant. Here's the story of how astronomers discovered the neutron star and what they learned about it. Neutron stars are pretty difficult to spot. They're incredibly small, just 20 kilometers in diameter. And they're faint because they're pretty far away. Most of them are located in the debris field of their exploded host star, known as a supernova remnant, where they're tough to see against the glowing gas and dust. Not to mention they spin pretty fast, emitting beams of radiation that pass over our line of sight more often than not. But this one happened to be aligned just right. In 2005, astronomers pointed Chandra at the bright supernova remnant M82. They knew there had to be something interesting in the middle of that cloud because the supernova remnant had an unusual shape with two lobes on either side of a jet-like feature in the middle. Something must have blasted a hole through the center of the debris field. But they didn't expect to find a neutron star. They just expected to find a black hole. The team was shocked when instead of a black hole, they found a neutron star. There are three main reasons why the team was surprised to see a neutron star rather than a black hole. The first has to do with the speed of the ejected material. Observations of M82 indicated that some of the material ejected during the supernova explosion was moving at 11,000 kilometers per second, which is fast. But that speed alone isn't enough to form a black hole. It would take speeds close to 20,000 kilometers per second to do that. The second reason is related to the mass of the neutron star. Since the star's mass determines whether it collapse into a black hole or stay a neutron star, the astronomers wanted to figure out how massive it was. They did this by measuring the wobble of the star's companion. Remember, this star was once part of a binary system. So after the initial explosion, what's left is a neutron star and a normal star orbiting around each other. The motion of the companion star tells us the strength of the gravitational pull it's feeling, and that in turn allows us to calculate its mass. The calculations suggested that the neutron star in M82 could be more than 1.35 times the mass of the Sun, which is well below the threshold for forming a black hole. The third clue comes from X-ray observations. Black holes emit no light, so you wouldn't expect to see anything if you looked at one with an X-ray telescope. Neutron stars, on the other hand, emit X-rays due to the intense heat of their surfaces. So when the Chandra team saw something, they knew it had to be a neutron star. Next, the team wanted to get a better look at the object, so they enlisted Hubble. This composite image is the result. The X-rays detected by Chandra are shown in purple and red, and the visible light detected by Hubble is shown in yellow and green. The swirling clouds of materials surrounding the neutron star are glowing gas heated to 2 million degrees by the intense radiation coming off the star. As the neutron star spins, its beams of radiation sweep across this material, causing it to glow. Some of the material is being pulled in by the gravity of the neutron star, while other material ejects outward, balancing each other. The inner regions of M82 are a battleground. Between the inward pull of gravity and the outward push of radiation pressure, one of the things that makes M82 interesting is that it seems to be in the process of shutting off. Most pulsars slow down over billions of years, but this one appears to be doing it in real time. M82 spins at 57% of the rate it would spin if it were a perfect sphere. As it radiates energy, it slows down. But unlike most neutron stars, whose spin down is too slow to notice, M82's is happening on a human timescale. In fact, the rate at which M82 is slowing down gives astronomers an estimate of how old it is. They think the star is somewhere between 3,000 and 4,000 years old. M82 is also special because it's one of the brightest neutron stars ever discovered. This is partly because it's relatively young, but it's also due to its distance. Astronomers think it might be the closest neutron star to Earth, at about 10,000 light-years away. The second nearest known pulsar is more than 5 times farther away. Being so close allows astronomers to study M82 in greater detail than any other neutron star. They've even been able to measure the star's spin down with great precision, allowing them to calculate the moment of inertia of the star. That's a measure of how much the star resists changes to its rotational speed. Knowing this property gives astronomers insight into what the star is made of. They can then compare this value to models of neutron stars to try to match them up. According to the best-fitting models, M82 is made up of mostly neutrons. But there's a small fraction of protons and electrons mixed in. Despite all this progress, there's still a lot astronomers don't understand about M82. We don't know exactly how fast it's spinning. It could be spinning faster than what Hubble and Chandra can resolve. If that's the case, it would mean that M82 is spinning more than twice as fast as the theoretical limit for a perfect sphere. We also don't know how fast the outer material is being blown away. With each rotation, millions of kilometers cubed of material is either falling onto the neutron star or being flung into space. We also have a lot of questions about what sparked the explosion that created M82. Astronomers know that it started out as part of a binary system, but that's about it. Now that astronomers have confirmed that M82 is a neutron star, they'll be able to learn even more about it. In the grand tapestry of the cosmos, few celestial objects captivate our curiosity as much as neutron stars. These enigmatic remnants of collapsed stars, also known as pulsars, are the densest known objects in the universe, boasting an incredible mass packed into a tiny space. Despite significant progress in unraveling their secrets, neutron stars continue to pose a multitude of mysteries that challenge our understanding of physics. From their formation to their bizarre properties, these celestial enigmas keep scientists on the edge of their seats, eager to unlock the secrets held within their enigmatic depths. At the heart of these mysteries lies the composition and structure of neutron star interiors. These celestial bodies are so dense that they defy conventional physics. As we delve deeper into their cores, we encounter matter in states that are not found anywhere else in the universe. One of the most intriguing questions is what happens to the building blocks of matter, protons and neutrons, under such extreme conditions. Do they retain their identity, or do they transform into exotic forms of matter? Some astronomers hypothesize that under extreme pressures and temperatures, protons and electrons could merge, giving rise to a soup of quarks. This revolutionary idea suggests that neutron stars could be composed of a different form of matter called quark matter, which could explain some of the observed properties of these enigmatic objects. But the existence of quark stars remains a subject of debate and research. Another mind-bending concept proposed by astronomers is the formation of nuclear pasta. Imagine long, thin strands of matter resembling spaghetti or lasagna sheets stacked together. Nuclear pasta arises from the unique properties of nucleons, the constituents of atomic nuclei. As these nucleons are squeezed together under extreme conditions, they form fascinating structures to minimize their energy. The competition between nuclear forces and electrostatic repulsion gives rise to these bizarre shapes. But how do these exotic forms of matter affect the behavior of neutron stars? Astronomers are investigating how nuclear pasta could influence the thermal conductivity and magnetic field evolution of neutron stars. By studying these effects, they hope to shed light on the cooling rates and X-ray emissions observed from neutron star surfaces. But the mysteries of neutron stars don't end there. Astronomers also want to determine the maximum mass a neutron star can attain before succumbing to the relentless pull of gravity. This is known as the maximum mass limit. According to theoretical calculations, the TOV limit, which is roughly 2 to 3 times the mass of our Sun, is the point beyond which neutron degeneracy pressure can no longer counterbalance gravity. If a neutron star exceeds this limit, it collapses into a black hole, leaving behind an enigmatic region from which not even light can escape. The study of neutron star mergers through gravitational wave astronomy is helping us probe this limit. By precisely measuring the masses and radii of neutron stars involved in these collisions, astronomers can test the upper mass limit. In fact, observations of PSR J0740 plus 6620, an incredibly dense neutron star about 2.1 times the mass of our Sun, are challenging existing theoretical models. Such discoveries are pushing the boundaries of our understanding and may provide insights into exotic physics beyond the standard model. The interior of neutron stars serves as a natural laboratory to investigate the behavior of matter under extreme conditions that are impossible. 2. reproduce on Earth by peering into these celestial objects. We gain a unique opportunity to explore the fundamental properties of matter and the forces that govern it. Neutron stars offer a one-of-a-kind setting to test the limits of nuclear physics. The extreme pressures and temperatures found in the interiors of neutron stars allow us to study the behavior of matter in conditions that are unimaginable on Earth. By observing the properties and characteristics of neutron stars, astronomers can gather valuable insights into the nature of matter at these extreme conditions. They can investigate topics like nuclear pasta and the behavior of matter at supernuclear densities. Studying these phenomena helps us better understand the fundamental constituents of matter and how they interact under extreme conditions. Neutron stars also provide a remarkable testing ground for theories related to nuclear physics and astrophysics. For example, the existence of quark stars, hypothetical objects that are composed entirely of quarks, can be investigated by studying the properties of neutron stars. By analyzing their mass, radius, and gravitational wave signals, astronomers can search for evidence that supports or refutes the existence of quark stars. Additionally, neutron stars serve as natural laboratories for studying phenomena like neutrino oscillations and the behavior of neutrinos in strong magnetic fields. These investigations can shed light on the elusive nature of neutrinos and their role in astrophysical processes. The extreme conditions inside neutron stars also make them ideal for exploring the behavior of matter under conditions that are typically found only in the early moments of the universe. By studying neutron stars, we can gain insights into the properties of matter during the formation of the universe. This includes understanding the behavior of particles like hyperons, which are hypothetical particles that contain strange quarks. Neutron stars, with their extreme conditions and exotic matter, present a unique opportunity to test the limits of nuclear physics. By observing and analyzing these celestial objects, we can explore the fundamental nature of matter and the forces that govern it, gaining insights that would be impossible to achieve on Earth. But wait, there's more. Astronomers have been puzzled by another peculiar feature of neutron stars: their ability to rotate at astonishing speeds. Some neutron stars, known as millisecond pulsars, spin hundreds of times per second. This raises a fascinating question. How do these rapidly spinning neutron stars maintain their stability and resist tearing themselves apart? To understand this phenomenon, astronomers study the rotational dynamics and stability of neutron stars. They investigate the factors that influence the rotational speeds of neutron stars, including their formation, accretion, and interactions with other celestial objects. By studying the stability of neutron stars, astronomers seek to understand the physical processes that prevent them from breaking apart due to centrifugal forces. One area of interest is the role of the neutron star's internal structure, including the possible presence of nuclear pasta. These unusual structures could affect the rotational stability by influencing the distribution of mass and the internal pressure. Additionally, astronomers study the interaction between a neutron star's rotation and its magnetic field. These interactions can lead to the formation of powerful jets of particles known as pulsars, which are observed as pulsating radiation from Earth. Understanding the interplay between rotation and magnetism helps astronomers to unravel the mechanisms behind pulsar activity. Moreover, the study of rapidly rotating neutron stars contributes to our understanding of general relativity. These objects rotate close to the theoretical limit set by general relativity, making them ideal for testing the predictions of Einstein's theory. By observing and analyzing the rotational properties of neutron stars, astronomers can refine our understanding of gravity and the nature of spacetime. And let's not forget about the extreme magnetic fields found near neutron stars. These regions, known as magnetospheres, are dominated by charged particles and electromagnetic radiation. Astronomers use sophisticated computational models to simulate the behavior of particles in these intense environments. By simulating the motion of charged particles in neutron star magnetospheres, astronomers can study the generation and propagation of electromagnetic radiation. They investigate the processes that lead to the emission of high-energy photons and the acceleration of particles to relativistic speeds. Through these simulations, astronomers can gain insights into the physical mechanisms that drive the extreme luminosity observed from neutron star-powered phenomena such as pulsars and magnetars. Understanding the particle acceleration processes in neutron star magnetospheres also helps astronomers study the interaction between these objects and their surroundings. By simulating the interaction of particles with the matter around neutron stars, they can model phenomena such as the ablation of stellar wind and the formation of accretion disks. These studies provide insights into how neutron stars shape their surrounding environments and influence the properties of nearby gas and dust. The mysteries of neutron stars continue to captivate astronomers, pushing the boundaries of our knowledge and challenging our understanding of the universe. The extreme conditions within these celestial objects provide a unique opportunity to study matter and the laws of physics in ways that are impossible on Earth. As we delve deeper into the secrets of neutron stars, we uncover the fundamental nature of our universe and our place within it. Neutron stars, with their enigmatic allure, serve as a reminder of the boundless wonders that await our discovery in the vast expanse of the cosmos. If you've enjoyed this video, I invite you to subscribe to our channel, where you'll find more captivating content on space, astronomy, and the mysteries of the universe. And if you have any thoughts, questions, or ideas you'd like to share, please feel free to drop them in the comments below. Your engagement is what inspires us to continue exploring and sharing these incredible discoveries with you. So join our community of space enthusiasts and keep looking up at the stars, because the universe never ceases to amaze. Thank you for watching. When you look up at the night sky, what do you see? Do you see an endless expanse of dark, empty space sprinkled with pinpricks of starlight? Or do you see something a little different, something a bit closer to home? What if I told you that the very ground beneath your feet is evidence of extreme cosmic events that happened before our solar system was even born? Welcome to Earth's Perspective, where we examine the universe on human scales. In this episode, we were going to consider the strange ways that neutron star mergers affect us here on Earth, and explore how one of the most extreme phenomena in the universe affects our everyday lives. When we think about the origins of the elements that make up our planet, our bodies, and even the devices we use, it's easy to imagine a slow, continuous cosmic process. Hydrogen and helium came from the Big Bang. Heavier elements came from stars. But the heaviest elements, like gold, platinum, uranium, and rare earth metals, have a much more dramatic origin: the cataclysmic mergers of neutron stars. Neutron stars are composed almost entirely of neutrons, densely packed into a tiny radius. When two of them collide, the gravitational energy released is enormous. In a fraction of a second, temperatures rise to billions of degrees, and neutrons are ejected into space at high speeds. This is the perfect environment for rapid neutron capture, known as the R process, a type of nucleosynthesis that forms the heaviest elements in the periodic table. Elements like gold, platinum, and uranium are created in abundance, then blasted into the interstellar medium. Over millions of years, these materials mix with gas clouds, seeding the formation of new stars, planets, and eventually life. In this sense, the gold in jewelry, uranium in nuclear reactors, and the platinum in electronics are all products of violent cosmic collisions. A humbling reminder that the most extreme events in the universe shape our everyday reality. Cosmic timeline. Imagine a cosmic timeline stretching from the beginning of the universe until now. At the start, around 13.8 billion years ago, we have mostly hydrogen and helium. It's the simple elements forged in the fiery crucible of the Big Bang. A billion years later, the first stars ignited, creating carbon, oxygen, and iron via nuclear fusion. Within the next several billion years, these stars lived out their lives and exploded as supernova, scattering these elements across space. Fast forward another billion or so years, and we see binary systems of neutron stars forming, destined to collide and produce even heavier elements. By the time our solar system formed around 4.6 billion years ago, these neutron star mergers had been happening for eons. Some of these heavy elements had already been produced, scattered by supernova, and mixed into the interstellar medium. Without them, Earth might lack the metals crucial for planetary geology, magnetic fields, and technological development. And there we are, zooming through time, arriving at the present day, where we marvel at the rich tapestry of elements that surround us, many of which were born in the cataclysmic collisions of neutron stars. Observational evidence linking collisions to Earth. For decades, scientists theorized that neutron star mergers were responsible for these heavy elements, but observational evidence was lacking. The watershed moment came in August 2017 when GW 170817, the first ever detected neutron star merger via gravitational waves, provided the key piece of evidence needed to confirm this theory. Scientists were able to confirm that the event did indeed produce heavy elements. Spectroscopic analysis of the material ejected during the merger showed the unmistakable signature of our process nucleosynthesis. Subsequent observations of other kilonovae have strengthened this link. It's widely believed that neutron star mergers may be the primary source of elements heavier than iron in the universe. Implications for life and civilization. The creation of heavy elements in neutron star mergers is not just astrophysical curiosity. It has profound implications for life as we know it. Let's begin with planetary formation. The cores of giant gas planets like Jupiter and Neptune are thought to have formed around the seeds of heavy elements. These elements also play a role in the generation of magnetic fields, which in turn influence solar system structure and habitability. On smaller rocky worlds, these elements can drive plate tectonics and shape a planet's surface. Take, for example, the rare earth metals, a group of elements with fascinating properties that are produced in significant quantities during neutron star mergers. These metals are vital components in modern technologies, from the chips in your phone to the lenses in your glasses. Without them, our digital age would grind to a halt. But their importance extends far beyond our modern conveniences. Rare earth metals are crucial in high-performance magnets used in everything from electric cars to wind turbines. They're also integral to the military and aerospace industries. One example is neodymium, an incredibly powerful rare earth magnet named for the Greek word neos, meaning new, and didymos, meaning twin. These magnets are a testament to the power of neutron star collisions. They're created by carefully combining neodymium with iron and boron in a complex manufacturing process. The resulting magnets are among the strongest in the world. A small neodymium magnet can lift over 200 pounds. That's enough to support the weight of an adult human. Now picture a world without these magnets, without the technology they enable. No electric cars, no efficient wind turbines, no advanced medical imaging equipment. Suddenly, the importance of neutron star mergers hits home in a very tangible way. But it's not just technology. Rare earth metals have biological importance too. Elements like molybdenum are essential for life. They form proteins in our body that transport oxygen throughout our blood. Without them, we couldn't survive. The story of technetium is equally fascinating. Created in neutron star mergers, it's the only naturally occurring element that doesn't occur naturally. All of its isotopes are radioactive, and it decays quickly, making it extremely rare on Earth's surface. Yet it plays a vital role in certain industrial processes. Its one application is in nuclear medicine. Technetium's short half-life makes it ideal for imaging and diagnostic procedures, allowing doctors to visualize and diagnose various conditions. Another use is in nuclear fuel. Barium, another element produced by neutron star mergers, is found in large quantities in the Earth's crust. It's used in the production of glass and ceramics, and is also employed in medical imaging. Interestingly, it was barium that was initially mistaken for radium in the famous Curie's laboratory when they were studying the mysterious new element. The influence of neutron star mergers on life and civilization. So let us move beyond the realm of individual elements and consider the broader impact of neutron star mergers on life and civilization. First, let's talk about uranium, the most well-known heavy element and the stuff of nuclear power. Uranium is a vital energy source for many countries, providing a significant portion of their electricity needs. It's used in nuclear reactors, where controlled fission reactions produce immense amounts of energy. But uranium's applications extend beyond energy production. It's also used in medical treatments, such as radiation therapy for cancer. Then there's gold, often associated with wealth and luxury, but its uses go beyond aesthetics. Gold is an excellent conductor of electricity and is highly resistant to corrosion. These properties make it invaluable in electronic components where reliability and durability are paramount. So as we navigate our daily lives, whether it's using a smartphone, powering our homes, or even receiving medical treatment, we're constantly interacting with the legacy of neutron star mergers. Their influence is deeply woven into the fabric of our existence. Even the very core of the Earth, where pressures and temperatures reach unimaginable levels, owes much to these stellar remnants. The Earth's magnetic field, which shields us from harmful solar radiation and allows for the existence of life as we know it, is partly generated by the movement of molten iron in our planet's outer core. This churning motion is driven, in part, by the heat produced by decaying radioactive elements like uranium, thorium, and potassium, all of which were forged in neutron star mergers. Neutron stars from Earth's vantage point. Considering neutron stars from Earth's perspective changes our understanding of the universe. They're not just distant curiosities. They shape the chemical evolution of galaxies. They connect the extremes of physics, the densest matter, gravitational waves, magnetic fields, to everyday materials on our planet. They remind us that our world is the product of both gradual cosmic processes and sudden, violent events. These stellar remnants in collision after collision have seeded our universe with the building blocks of life, linking the tiniest subatomic particles to the very rocks beneath our feet. Next time you gaze up at the stars, remember that you're seeing not just points of light, but remnants of ancient collisions, cosmic furnaces where the heaviest elements were forged. You're witnessing the birthplaces of the materials that make our modern world possible, reminding us of the intimate connection between the grand events of the cosmos and our lives here on Earth. Humanity's gaze. How we see neutron stars. Despite their tiny size, typically only about 20 kilometers in diameter, are among the most extreme and fascinating objects in the cosmos. Observing them, however, posed a monumental challenge. They are dense, distant, and often invisible in ordinary light. To study these exotic objects, humanity had to invent new ways to see the universe, venturing into wavelengths beyond visible light and detecting phenomena that had previously been entirely theoretical. The discovery that changed everything, the story begins in 1967. The University of Cambridge, where Jocelyn Bell Bernal, then a graduate student, meticulously analyzed miles of pen-chart recordings from a radio telescope. Amidst the noise, she noticed an unusual, regular pulsing signal, repeating every 1.337 seconds. Initially dubbed LGM-1, Little Green Men. For its seeming regularity, it soon became clear this signal was not a message from extraterrestrials, but the signature of a rotating neutron starlater called a pulsar. Bell's discovery was revolutionary. It was the first direct observational evidence of neutron stars, confirming theoretical predictions made in the 1930s by Lev Landau, Walter Baade, and Fritz Zwicky. Pulsars, as these objects were named, emit beams of electromagnetic radiation from their magnetic poles. As the neutron star spins, these beams sweep across space like a cosmic lighthouse, producing the precisely timed pulses detected by radio telescopes on Earth, X-ray and gamma-ray astronomy. Seeing the invisible while radio observations revealed pulsars, other neutron stars remained hidden. Many neutron stars are extremely hot, emitting primarily in X-rays or even gamma rays, invisible to optical telescopes. This realization led to the development of space-based observatories, free from Earth's atmosphere, which absorbs high-energy photons. Key instruments include Chandra X-ray Observatory, launched in 1999, provided unprecedented resolution of neutron star surfaces, pulsar wind nebulae, and supernova remnants. XMM Newton, complementing Chandra, it offered large-area X-ray spectroscopy to probe the chemical composition and thermal properties of neutron stars. Fermi Gamma Ray Space Telescope, detecting gamma-ray pulsars. It unveiled rapidly spinning neutron stars invisible in radio wavelengths. These telescopes revealed phenomena like magnetar flares, X-ray bursts, and pulsar glitches, offering direct insights into the physics of neutron star interiors, magnetic field dynamics, and rotational behavior. Gravitational wave astronomy. Listening to the cosmos in 2015, humanity entered a new era of neutron star observation, gravitational wave detection. When neutron stars collide, they generate ripples in spacetime. Detected by facilities like LIGO and Virgo, the 2017 event, GW170817, is a watershed moment. For the first time, astronomers observed a neutron star merger via gravitational waves, gamma rays, and visible light simultaneously. This multi-messenger approach provided a holistic view, confirming that mergers produce heavy elements via the R process. measuring the equation of state of dense nuclear matter, demonstrating the power of coordinated multi-wavelength observations in modern astrophysics. Gravitational waves have opened a new dimension, allowing us to hear neutron stars, complementing the light we see through traditional telescopes. Simulations and theoretical modeling, human ingenuity, also extends to computational astronomy. High-resolution simulations model neutron star mergers, magnetosphere dynamics, and pulsar winds, revealing complex behaviors impossible to witness directly. These simulations, informed by observational data, allow scientists to predict gravitational wave signals for future detectors, understand the internal structure and magnetic field evolution, explore hypothetical phenomena such as quark star formation or exotic superfluidity. The synergy between observation, theory, and simulation exemplifies modern astrophysics. We cannot travel to these stars, but we can reconstruct their reality with exquisite precision. Human curiosity and cultural impact, neutron stars have captured not only scientific attention, but also public imagination. Pulsars, magnetars, and mergers have inspired science fiction, philosophical reflections on extreme physics, and the idea that even the densest, most remote objects in the cosmos affect our understanding of reality. From Bell's painstaking radio analysis to state-of-the-art space observatories, humanity has continually expanded its gaze into the universe, turning what was once invisible into observable science. Neutron stars are proof that curiosity, persistence, and technological innovation allow us to probe the most extreme corners of the cosmos. Future implications in our placing the grand tapestry of the cosmos, neutron stars have emerged as both enigmatic outliers and vital threads, connecting realms of physics once thought disparate. Their study has not only reshaped our understanding of stellar evolution and the fundamental laws of nature, but also illuminated our place within the universe. Looking ahead, several key areas hold immense promise for advancing our comprehension of these celestial enigmas. First and foremost, the next generation of gravitational wave interferometers promises to revolutionize neutron star research. Advanced LIGO and Virgo detectors, along with new players like the Korean Kagra and the Japanese LSC, will boast increased sensitivity, enabling the detection of fainter signals and more distant events. This enhanced capability will facilitate the study of individual pulsars in binary systems, shedding light on their formation and evolution within close stellar partnerships. Furthermore, it will enable the observation of lighter neutron star mergers, providing valuable insights into the R-process nucleosynthesis and the behavior of matter under extreme conditions. Multi-messenger astronomy, a coordinated observation of celestial events across the electromagnetic spectrum and gravitational waves, has emerged as a powerful tool for unlocking the secrets of the cosmos. By combining data from various sources, astronomers can piece together a comprehensive picture of neutron star mergers, their progenitors, and their aftermath. For example, the joint observation of gravitational waves in gamma-ray bursts has provided crucial evidence for the merger scenario of short gamma-ray bursts, linking these enigmatic phenomena in an unexpected way. As our understanding of multi-messenger astronomy grows, so too will our comprehension of neutron star behavior and their broader implications for the universe. Numerical relativity and astrophysical simulations play an increasingly pivotal role in interpreting observations and predicting outcomes. Sophisticated computer models allow scientists to simulate the dynamics of neutron star mergers, the behavior of matter under extreme conditions, and the evolution of neutron stars over time. These simulations, often coupled with machine learning techniques, provide invaluable insights into the physical processes at play, aiding in the interpretation of observational data and guiding future research endeavors. Moreover, the ongoing development of theoretical frameworks and equations of state for neutron star matter is essential for constraining models and interpreting observations. As our knowledge of nuclear physics and astrophysics advances, we refine our understanding of the matter that constitutes these celestial objects, providing a deeper insight into their stability, structure, and behavior. International collaboration and the sharing of data and resources are vital for advancing our understanding of neutron stars. By pooling our collective expertise, observational capabilities, and theoretical frameworks, we can tackle the complexities of these fascinating objects more effectively. Initiatives like the Einstein Telescope propose third-generation gravitational wave observatory, exemplify the global commitment to unraveling the mysteries of neutron stars and their role in the cosmos. In conclusion, the journey of discovery regarding neutron stars has been nothing short of extraordinary. From their initial identification as pulsars to the exploration of their gravitational wave emissions and multi-messenger signals, each milestone has deepened our understanding of the fundamental laws of nature. As we stand on the threshold of new observational capabilities and theoretical advancements, we are poised to unlock even greater insights into the behavior of matter at extreme densities, the nature of gravity in extreme environments, and the origin of heavy elements in the universe. Moreover, the study of neutron stars offers a unique opportunity to understand our place within the vast expanse of the cosmos. By probing the properties and behaviors of these extreme objects, we gain insights into the evolution of massive stars and the nucleosynthesis of heavy elements, processes that have shaped the chemical abundance of the universe. Furthermore, the detection of gravitational waves from neutron star mergers has provided a new window into the study of general relativity and strong gravitational fields, allowing us to test the limits of Einstein's theory and deepen our understanding of gravity itself. Finally, the quest to understand neutron stars transcends the boundaries of scientific inquiry. It touches upon fundamental questions about the nature of reality, the limits of human knowledge, and our place in the grand scheme of the cosmos. The enigmatic allure of these celestial objects continues to inspire wonder and curiosity, reminding us of the boundless potential of human ingenuity and the enduring quest to unravel the mysteries of the universe. The dead stars' gifts. How neutron stars enriched our world. Neutron stars. The dead cores of massive stars have been called everything from exotic laboratories to celestial lighthouses. But perhaps their most intriguing title is that of gift givers. These remnants, smaller than a city yet more massive than the sun, play a pivotal role in the universe's chemical activity. They don't just enrich space with elements crucial for life, they also seed the cosmos with the building blocks of planets, potentially impacting the formation of worlds beyond our own. The story begins with the death throes of massive stars. When such a star collapses, its core implodes, triggering a supernova explosion. During this cataclysmic event, elements like iron and nickel are forged in the star's core, creating the raw materials for planets and life. But the real magic happens after the star's death. Enter neutron stars, the incredibly dense cores left behind. Their influence extends far beyond their small size. When two neutron stars merge, they produce a spectacular show, releasing huge amounts of energy and radiation. This event not only creates ripples in spacetime known as gravitational waves, but also triggers explosive nucleosynthesis. In simple terms, the merging neutron stars produce a burst of energy so powerful that it creates heavy elements from lighter ones. This process, known as the rapid neutron capture process, or R process, is responsible for creating many of the heaviest elements on the periodic table, including gold, platinum, and uranium. These elements are not just interesting oddities. They are essential components of our world. Gold, for instance, has numerous technological applications, from electronics to medicine. Uranium, with its ability to sustain nuclear fission, provides a significant energy source, and platinum's catalytic properties make it invaluable in various industrial processes. Without neutron stars and their dramatic mergers, the universe would be a much less glittering place. Lacking the diversity and richness of elements that make our modern world possible. Moreover, neutron star mergers are believed to be the primary source of the R process elements, meaning that without these cataclysmic events, the universe would not have enough of these essential elements to support advanced technology and life as we know it. Neutron stars thus serve as both the creators and preservers of these vital resources, shaping the universe in ways that extend far beyond their immediate surroundings. Understanding these stellar remnants not only helps us comprehend the fundamental laws of physics under extreme conditions, but also reveals the intricate workings of our own planet and the potential for life elsewhere in the cosmos. The gifts of neutron stars, once thought to be mere curiosities, are now recognized as fundamental to our existence and the evolution of our universe. Now let's move on to the next chapter. Neutron Star Laboratories. Testing physics at the edge of knowledge. Neutron stars. With their extreme conditions of temperature, pressure, and gravity, offer a unique platform for testing our understanding of physics. By studying these celestial bodies, scientists can validate or refine theories that govern the behavior of matter and energy in the most extreme environments imaginable. One of the primary areas where neutron stars serve as invaluable laboratories is in the study of nuclear physics. The interiors of neutron stars, subject to immense pressures and temperatures, allow researchers to explore the behavior of matter in conditions that cannot be replicated on Earth. For example, neutron stars help scientists study the properties of neutron-rich nuclei and the processes that occur in their synthesis. By analyzing the spectra of elements produced in neutron star mergers, astronomers can test theories related to the structure of atomic nuclei and the forces that bind them together. Another crucial area where neutron stars contribute significantly to our understanding of physics is in the realm of particle physics. The intense magnetic fields found near these objects provide an ideal setting to examine the behavior of particles and radiation. By observing how particles interact with the intense magnetic fields around neutron stars, scientists can test theories related to fundamental particles and their properties. Furthermore, neutron stars serve as natural laboratories for testing general relativity, Einstein's theory of gravity. Their extreme masses and rapid rotations create strong gravitational fields that allow astronomers to study gravity under conditions that are not achievable on Earth. By observing the behavior of neutron stars, scientists can test the predictions of general relativity, such as the bending of light around these objects and the properties of gravitational waves emitted during their mergers. Moreover, neutron stars provide a unique opportunity to investigate the behavior of matter in extreme gravitational fields. By studying how matter is affected by the intense gravity near these objects, researchers can test theories related to the nature of spacetime and the behavior of particles under extreme conditions. Additionally, neutron stars serve as natural laboratories for studying plasma physics, as their hot and dense atmospheres consist of ionized gases that exhibit collective behavior known as plasma. By observing the behavior of the plasma around neutron stars, scientists can study various plasma phenomena, such as magnetic field generation and energy transport, which have applications in various fields, including astrophysics, fusion energy, and space propulsion. Overall, neutron stars serve as extraordinary laboratories for testing physics, because they offer conditions that are not achievable on Earth. By studying these celestial objects, scientists can validate or refine theories that govern the behavior of matter and energy under extreme conditions, leading to a deeper understanding of the fundamental laws of nature. Now let's continue with the next exciting chapter: neutron stars and the future of physics, exploring the unknown through extreme objects. Neutron stars, the dense remnants of collapsed stars, are not just fascinating astronomical objects. They are also key to unlocking mysteries that stretch the boundaries of our current understanding of physics. By delving into the nature of these extreme objects, we can gain insights into some of the biggest unanswered questions in physics, from the behavior of matter at extreme densities to the nature of gravity and the origins of heavy elements. One of the most compelling aspects of neutron stars is their potential to revolutionize our understanding of nuclear physics. The interiors of neutron stars are so dense that they challenge our current models of how matter behaves. By studying the properties of neutron stars, we can test the limits of nuclear physics and gain insights into the behavior of matter at unimaginable densities. Additionally, neutron stars play a crucial role in our understanding of the origin of heavy elements. The ARC process, which occurs during the merger of two neutron stars, is responsible for producing many of the heaviest elements on the periodic table. Studying these processes not only helps us understand the evolution of galaxies, but also sheds light on the conditions that led to the formation of elements essential for life. Neutron stars also offer a unique opportunity to test Einstein's theory of general relativity, which describes the nature of gravity. By observing the behavior of neutron stars, we can look for deviations from Einstein's predictions and gain insights into the nature of gravity under extreme conditions. Moreover, neutron stars are closely tied to the phenomenon of gravitational waves, ripples in spacetime that were predicted by Einstein a century ago. The merger of two neutron stars produces a distinctive gravitational wave signal that provides a unique window into the behavior of matter under extreme conditions. Analyzing these signals can help us understand the dynamics of neutron star mergers and test our theories of gravity. Furthermore, neutron stars are associated with some of the most energetic explosions in the universe, such as supernovas and gamma ray bursts. Understanding the physics behind these explosions not only helps us understand the life cycle of stars, but also sheds light on the behavior of matter and energy under extreme conditions. Finally, neutron stars are closely related to black holes, the most extreme objects in the universe. By studying the boundary between these two types of objects, we can gain insights into the nature of black holes and the fundamental laws of physics. In conclusion, neutron stars are not just fascinating objects of study, they are key to unlocking some of the biggest mysteries in physics. By exploring the nature of these extreme objects, we can test our current understanding of the universe and pave the way for new discoveries that could revolutionize our conception of the physical laws that govern reality. So keep looking up and let your curiosity guide you as we continue to unlock the secrets of the cosmos. If you enjoyed this video, be sure to subscribe for more. Don't forget to hit the bell icon to stay updated on our latest content. If you're passionate about space and eager to learn more about the wonders of the universe, we invite you to join our community. With a shared passion for space exploration and discovery,